All right, hello class. In this particular video, we're going to be finally starting to answer those questions, or at least start approaching some of those concepts I mentioned early on, which is what Cal 3 really is all about, is moving things into multiple dimensions. So specifically, this lesson from the book is called Lines and Curves in Space. I like to think of it as specifically we're talking about vector-valued functions. Okay, or sometimes you'll just hear me say vector functions, since saying vector-valued functions is kind of a mouthful. Vector-valued functions are basically, well, if we put numbers in our vectors before, like 2, 3, for example, there's nothing stopping us from saying instead having a vector, let's say 2t, comma, let's say 3t squared, right? And so we're going to actually discuss what exactly is going on here, and what it looks like, how to analyze it, how to take a look at it, so on and so forth. All right, so back in our Cal 1 days, right, and this would be Cal 1 and Cal 2 days, we were basically only looking at things like f of x, or y equals f of x, right? We would have one independent variable, which would be our x, and we would have one dependent variable, which would be our y. Okay? Well, what vector-valued functions do is they instead create a function, let's say v of t, which can either be a function that is basically a vector where I'll have x of t, y of t. Or you could also have a function in a vector x of t, y of t, z of t. Okay, so what's going on here is we are creating a situation where we will still have one independent variable, right, and that's going to be our t, but we will have 2 to 3 dependent variables. That would be, say, x, y, and sometimes z. So before, we always assumed, well, maybe not always, but we usually assumed that, say, y was dependent on x, right? So as x behaved in some way, y would follow along. So something like y is equal to x squared. Okay, so that's our Cal 1 world, our Cal 2 world. That's our typical, one-dimensional kind of ideas that you've studied in calculus and pre-calculus and algebra and with limits and all sorts of things. Whereas here, what we're doing is now we're not saying y depends on x. So we're no longer saying that y depends. Okay? What we're saying instead is that y and x and z, if we're talking about 3 dimensions, are independent of each other. However, they all depend on t. So they all depend on the same independent variable t. All right, so how I think about this is I think about always a bug on, say, a piece of paper or on your wall or on the board if I'm teaching in a physical classroom. Okay, so you can think about the bug. Let me make him green. Right, say a bug is crawling around on the wall, and maybe the origin is the corner or what have you, but at each particular time, say at t equals 0, it's going to have a specific point in space. Right? But as time goes on, maybe it moves around. Right? So maybe at t equals 1, and let's say we're in minutes, at t equals 1 minute, now the bug has moved over here. Okay, so it will be at a different point, or maybe it won't be. Maybe it will, sorry, these should probably be x naught, y naught, and this would be x1, y1. Okay, and at each time value, it's going to be at a different point. So this might be the point it's at when t is equal to 0.5. Right, now as the bug moves around, right, so this might be t equals 10 now. Okay, so the idea is that at each time value, the bug is at a specific point in space, and it's the point that is changing as time changes. Okay, so the big difference between vector-valued functions, also known as parametric equations, is this idea of motion. Right? There is implicit motion involved here. Right? Because as t changes, x, y coordinate at each time. So the question really becomes, well, how do vectors come into this, right? We started with the vectors, and it comes in this way. If we have what are called parametric equations, and where that word comes from is the word parameter. So the parameter is t. T is the parameter. That's the thing that's changing. And so what ends up happening is we have that our x is a function of t and y is a function of t. Right? And for each t, we get a unique point. Right? X comma y, or f of t comma g of t. So the question is, well, why do we even bring vectors into this? And it really comes down to the fact that adding points doesn't make any sense, right? Adding points doesn't give us anything, whereas adding vectors does. We don't have algebra of points. So instead, we move this to vectors. And it also gives us something interesting, because when we represent this in terms of vectors as functions, we actually get a vector that points along the trajectory of the path. Okay, so in other words, at each time, we can actually think of a vector pointing to where the bug's position is. Now, I'm going to give a better example of this in just a second. Okay, but the reason we do this is really just because we get algebra with vectors, that it's really useful, and it will be super useful once we start actually applying calculus to this. Okay? All right, so let's look at an example, and it's much easier to talk about this with an actual example where we can look at a graph. All right, so here's a pretty basic example. The example here is the vector function r of t equals the vector t squared comma t. All right, so my first advice to everyone when they're first dealing with vector valued functions is to actually make a table and then fill out that table to give you the points at each time. All right, so here I'll bring up an example real quick. Okay, so we have our t values are given to us, 0 to 4, and I'm just going to go through and start plugging these in. Well, for x, what's happening to x is t squared, so we're just going to take the t and square it. So we'll get 0, 1, 4, 9, and 16. Whereas y is just t, so that's actually just going to spit out t again. So we'll get 0, 1, 2, 3, 4, and then giving us the point 0, 0, 1, 1, 4, 2, 9, 3, and 16, 4. Well, actually, I say it gives us the point, but really what it's spitting out is the vector. All right, so it's actually the vector 0, 0, the vector 1, 1, the vector 4, 2, the vector 9, 3, and the vector 16, 4. Well, okay, what does this look like on the graph? So let's take a look at a graph. Okay, so here we have a graph prepared. When t is equal to 0, the vector is just 0, 0, right? But when t jumps up to 1, we get the vector 1, 1. When t goes to 2, we get the vector 4, 2. 3, we get the vector 9, 3. And 4, it's right up the screen here, but we get the vector 16, 4. Okay. So what this is doing, you know, it's not exactly in terms of vectors all that interesting, but what this is doing is actually tracing out the trajectory of that of an object moving through space. So let me show you the trajectory, and when we slow down the time step, hopefully it will show you what's going on, because what these vectors are doing are pointing to where that object is in space at each particular time. All right, so here we are with the trajectory pathed out, and it maybe seems a little like, okay, are we actually sure about this? But if I shrink down the time step, it will actually look a lot smoother. Okay, so now I've shrunken down the time step to be about 0.25, and hopefully, since this is a little smoother, it actually looks like, or at least closer to what this curve is doing. And if I reduce it down a little bit more, okay, so now I've reduced it down by a lot, and now I'm letting it animate, and as we can see, we are getting that trajectory. And it's going back. Let me keep it from doing that. There we go. All right, so as you can see, the vector in orange is tracing out the trajectory, which we're mapping out in blue there. All right? Okay, so this is essentially what vector-valued functions do. They trace out a trajectory of an object in time. So at each time we get a specific point, xy coordinate, and this is basically telling us you know, the trace of the object. Now if we get rid of the vector, all we're left with is the trajectory. Okay, which is really what we concern ourselves with. However, there always is that vector there pointing to the right coordinate. All right, now if I study this a little closer, so what I've done is we're basically letting x be t squared and y be t. Well, if y is t, we can actually plug it in to here to bring this back to x equals y squared, right? So this now is a formula we're a little more used to. This is a sideways parabola. Or we can think of it as this, y equals plus or minus the square root of x. And that is how you would graph it, say, in your graphing calculator, like if you have a TI 83 or something, right? It doesn't play well with this, but it will play with this. So this here, this is called a Cartesian equation. Right, and where that word comes from is from the mathematician and philosopher Descartes, Cartesian. He's the philosopher known for coining the term "I think, therefore I am." Very interesting fellow, but he was also a mathematician, and he was influential in the idea that we can represent algebraic concepts on a grid, x by y. That's why it's called the Cartesian coordinate system. So what we've done here is we've basically turned this into a Cartesian equation, whereas this is considered either a parametric equation or a vector-valued function, right? Okay, and so here's the graph of x equals y squared. Again, if you did y equals plus or minus square root of x, this would be the plus square root of x, this would be the minus square root of x, but we're looking at x equals y squared. So if I bring back the vector-valued function here, what we'll notice is that this vector-valued function, let me bring back the t-value as well. Here we go. So as time is going forward, we'll notice that what we're doing is this guy is traveling along this path. Okay? Now, if we change just the t's, so notice if I go back here, I'm letting t go from 0 to 4, but if instead I looked at, I don't know, t equals maybe -2 to 2, we would get the following. Okay, so here we go with t starting at -2 and going to +2. So we'll see that we start here and we're moving through the origin and up this way. So the thing about parametric equations of vector-valued functions is there, as I mentioned before, is implicit motion. Motion is implied here. Okay? So, and we'll notice that there's actually a bit of a velocity sort of going on here because it seems to slow down here and then start speeding up. See, it starts up kind of fast and then it starts to slow down a bit and then it starts to pick up again. And so let me bring the vector back, and the vector the whole time is pointing at where the object is in space at that moment. And I'll just let it go through one more time here. Okay, so the important thing I want to mention, or to really drive home the fact, is this Cartesian thing here, I consider that the path, right? That's the path that the object is, or the bug, say, is walking along, and the vector-valued function describes how the object travels along that path. All right, so a Cartesian equation, like x equals y squared, describes the path that the bug is traveling on. Okay, while the vector-valued function describes how the bug travels, right? How fast is it going? What direction is it traveling in? What's its starting point? What's its ending point? Etc., etc., etc. So that looks more like this. The vector-valued function r of t is equal to the vector t squared comma t. And as we saw before, we got different paths depending on if we went from 0 to 4 or -4 to 2. Okay. All right, so let's take a look at another example, and I'm going to look at s of t equals the vector-valued function t comma square root t, t going from 0 to 16. Now, you may notice here that I actually haven't done much except replace my t's with square root t's. Okay, but if you don't see that, you probably will in a second when I go to graph this. So let's take a look at a graph of this. Again, we would do it the same way. You could make your table, you could just graph it. All right, so here we go. I've set this up to graph the vector-valued function s, and we'll notice that you'll notice one, I left the path there, and we see that we're moving along the same path. However, there is a difference, and it's how quickly we're moving through it. All right, so let's take a look at R and S moving together. And let me slow this down a little bit. All right, so as we see, at the beginning, R is going a little slower than S, but then R starts speeding up and speeding up and speeding up and speeding up, and S is traveling along the exact same path, but going slower. Okay, and it too should be speeding up as time goes on, but R is outclassing it by a lot. So we start this over again. Okay, so this is what I mean by the fact that the Cartesian curve gives us the path, but the vector-valued function tells us how we travel along that path. Okay, so if I do something a little crazier, like instead I make a vector-valued function w of t, which is sine squared t comma sine t, notice again, all I'm doing is just taking that same pattern we started with, this r of t equals the t squared comma t, and just changing what's being squared and the t, right? I'm replacing the t with sines. Now, what we know about sine is that it oscillates, right, between -1 and 1. And so when we look at the graph of this, we should see some of that behavior. All right, so if we take a look at the graph of w, and again, I recommend taking a look at a table, but it starts at 0, moves up to the point 1, 1, then starts moving back down to the point 1, -1. And we'll go back and forth along this same path, right? The path is the same, but how it's being traveled is different. Okay, so, and that is the basic idea of how vector-valued functions work. And there are lots of crazy, bizarre things we can do, because it turns out that this right here is a function in the terms of vector-valued functions. Even though it fails the vertical line test, we're not in the Cartesian space anymore. Now it fails, or it satisfies what we would call the t-test, or the time test. For every time, there's a unique x and y coordinate. The only thing that would cause it not to be a function is if at a particular time the bug split and was at 2 different points, but that's not going to happen unless it's some sort of crazy quantum bug. Okay, so let's look at another example just to show an idea of all the funky things you can do with these, and then we'll start talking about how we can use them. Okay, so here I'm looking at r of t equals 4 sine of 2t over 3, comma 3 sine of t, and we get this neat looking thing here. Okay, and I'll speed it up a little bit. Okay, so there we go. And if it would just continue along this path, I'm pretty sure it just sort of repeats this over and over again. Okay, so now I've adjusted it a bit. To instead of 2/3 inside a sine, it's just 1/3. And this is actually kind of interesting here. It just goes back and forth along this particular path. All right, so here I'm putting a 5/3 in, and we see this particular behavior here. All right, and finally, let's put a, oh, that's not right, hang on. I put a 3/4 in. There we go. And it gives us this. I'm going to speed it up a bit. Okay, so the beautiful thing about vector-valued functions and parametric equations is it gives us an ability to model objects that are flying around in space, curves in space, for example, and it allows us to talk about the formulas we already know fairly well and give it motion, right? Give it a way to describe how it moves along a path, not just what the path is. All right, so let's talk about some of the important vector value functions that we should be able to just create when needed, because we will need to do this at some point. So when we want to do lines, and specifically a line segment going from A to B, how we typically want to do this is we usually want our starting point at t equals 0 and our ending point at t equals 1. All right, so we want to cruise through this line in 1 unit of time. All right, and one of the most common questions I get when it comes to lines is why is it 0 to 1? Do we have to do it that way? And ultimately, the answer there is no, we don't have to. But we do, because in the future, this is going to make our life way easier to deal with. Okay? All right, so let's take a look just at a particular example. Let's say we're starting at the point, this looks like 1, 2, and we want to move to the point, this looks like maybe -3, -1. Okay, so we want at t equals 0 to be at this point 1, 2, and when t is equal to 1, we want to be at this ending point, -3, -1. All right, so here's the quickest way to do this as a vector valued function. Okay, in general, your r of t, okay, is going to be x naught plus delta x times t, and y naught plus delta y times t. All right, and the reason that works is what we're doing is this. We're letting x be, and specifically this will only work if we're letting t go from 0 to 1. But when x is equal to x naught plus delta x times t, and y is equal to y naught plus delta y times t, well, what we can actually do is solve this equation here in terms of t. And this is actually what's called eliminating the parameter. Okay, eliminating the parameter, because what's going to happen when we solve for t, so now I'll divide by the delta x. What we've done is we've solved for t. We have that t is equal to x minus x naught all over delta x, and this t we can plug into here and there, and get a formula that's just in terms of x and y. So we can get this down to be y is equal to y naught plus delta y times x minus x naught all over delta x. Okay, this has now become a Cartesian equation. And that's what eliminating the parameter is you try to solve things to get it down to being just in terms of x and y, versus a parametric equation, which is both in terms of, well, it's just in terms of t, but you have your x in terms of t and your y in terms of t. Okay, now if I do a little bit of work here, if I say factor this delta x out and move this y naught over, we're going to get y minus y naught is equal to delta y over delta x times x minus x naught. And hopefully that's familiar to you all as the point slope form of the line, because we have delta x over delta y is our slope. Okay? Oh, well, if we have our we have our original points here, okay, if our starting point is 1, 2, well, and this case, that is going to be our x naught, y naught. So that's what's going to go in here. So if r is x naught plus delta x times t, comma y naught plus delta y times t, okay, our starting point is the x naught, y naught. When we're in Cartesian form, we have a little bit of leeway. We can choose what point we want to be the starting point or the ending point. In this case, we can't because we're told we're moving from one point to the other. Okay, so our x naught here is 1, and our y naught here is 2. Okay. Now, when I say delta x, I'm talking about how much x changes from this point to this point. So we're going from an x equals 1 to an x equals -3. So 1, 0, -1, -2, 3. So that would be 4. The quick way to, or -4 since we're going in the next negative direction, but it's going to be the -3 minus 1 times t. It's that difference, right? The delta x. And for the delta y, we're going from 2 to -1. So 2, 1, 0, -1. That is also -1 minus 2 times t. Okay, so it looks like we get down to 1 minus 4t, comma 2 minus 3t. Okay, and again, this is just the simplest way to go about it. All right, so let's take a look at this on a graph and see if it aligns with what we see here. Okay, so here we have our points A and B. Let me do this. Okay, so the point 1, 2, here's the point -3, -1, and then here's the vector valued function we created along with its trace, and let's look at it from t going from 0 to 1, and as you can see, what the vector r is doing is pointing along the line that goes from A to B. Okay, now if we want to go from B to A, that it's not the same formula. Okay, you can't just negate the function. Okay, you have a whole nother starting point. So here, your x naught would be -3, and your y naught would be -1, right? You're starting at a different place, and your slopes are going to be different, but they should be the same magnitude. They should be the same number because here your x goes from -3 to 1, so it'd be 1 minus a -3t, okay, and then -1 plus, now it will be 2 minus a -1t. Okay, so it will end up being -3, and this will be plus 4t, and then -1 plus 3t. So as we can see, the number itself is the same in the slope portion of it, but we have a different starting point. And then here they are on the graph, or this S that we just created. Okay, so to go in the opposite direction, it's not just a matter of like negating everything. You have a different starting point. All right, so that's how you deal with lines, and it works in 3 space as well. All right, so that's lines. The next big one is circles. And how we end up doing circles is, all right, if we have a circle centered at the origin with radius r, let's say, okay, its formula in the Cartesian form is x squared plus y squared is equal to r squared. Okay, so that's how we deal with that. Now, how we move this to parametric equations or as a vector-valued function, well, you could think of the radius at each time step actually pointing at a place on the graph. Now, how we get this point on the circle, we can actually do that through the angle, which I'm going to let the angle change through time, right? Because as time increases, I'm going to let the angle increase. Well, how that works is any point on a circle centered at the origin is going to be r cosine theta, comma r sine theta, right? We've seen this before in this vector. Let's call it, let's not call it r. Let's call it s, okay? So s is going to be the vector r cosine t, comma r sine t, right? And if we want the full circle, we're going to do 0 to 2 pi in our t's, okay? So, now, this gives us the circle centered at the origin, oriented counterclockwise with radius r. Okay, so to give an example of that, let's take a look at the graph 5 cosine t, comma 5 sine t. For t, going from 0 to 2 pi. All right, so when we go to start graphing this, like when we plug in 0, cosine of 0 is 1, sine of 0 is 0, so we would get the vector 5, 0. Okay, and then we start just going from there, and I'm doing it in steps of basically pi 50ths looks like the steps I'm taking here, and you can see that when we do this, we get a circle. Okay, now if I instead change let's look at what happens when we start changing things. Okay, so here is the vector-valued function we're talking about. Let's see what happens if I put negative t's in. Okay, so now we'll have 5 cosine negative t, 5 sine and negative t, and when I start the animation now, notice it's the same circle, we're just going clockwise through it instead of counterclockwise. That should make sense because instead of putting in something like here, pi over 2, we would have negative pi over 2. All right, let's step back to the normal positive guys. Okay, and let's see what happens if I actually change one of these values here. So instead of 5 cosine t, let's make that, let's say, 3 cosine t. All right, there we go. There's 3 cosine t, comma 5 sine t, and you already notice that the vector s doesn't start over here at 5, 0. It starts here at 3, 0. Well, when we let this go, we'll see, oh, in the x direction, we get 3 but in the y, it still goes to 5 and -5. This makes an ellipse. So this makes an ellipse where the number in front of cosine gives us the x radius, so to speak, and the number in front of the sine gives us the distance we go in the y. So that gives us a really quick way to do ellipses as well. All right, so let's say that we want to actually change the center of a vector valued function. It's as simple as throwing in an x naught and a y naught, just like we did before with the lines. We can do that as well with circles and really anything we want. If we want to change that starting position, we just throw in a plus x naught and plus y naught. And as you can see here, what I've done is put a +3 and a -2. And so that is going to change the center from 0, 0 to 3, -2. All right, trying that again. So as we can see here, I've put the +3 and the -2, and you'll notice that the vector s is actually pointing somewhere else. It's actually pointing at the starting position that we would get now that we've moved the center to 3, -2. So at 3, -2, here's the center. Here's the radius at 3. Okay, so we're actually going to get it tracing out the circle at this new center. So as you can see, we still have the circle radius 3, but now it is centered at the point 3, -2. And as you can see, what I think confuses people with this a lot when they're first studying it is notice that the vector itself is not coming from the center of the circle. It's still pointing out from the origin, just at the path that the, say, object is traveling. Okay, so for right now, I think this is probably enough brain melting for one video. I'm going to come back with a part 2 of this where we start looking at how this stuff works in 3 dimensions. All right, and then we'll start looking at the calculus of this stuff, because how the actually that would be a good thing to show here is how the different speeds work. So given what we have here, if I were to put something slower in the t's, you'll see a slower travel along the circle. All right, so here's a graph I've put together, excuse me, where I have this one in pink where I replace the t's with square root t's, and you can see how much slower it's going around the circle compared to our original one here. So this is where the calculus comes in. We can use calculus to analyze how quickly or how slowly or the rate or the velocity of objects are moving along a path. Okay, and that's what we'll be doing in the next section. Of course, first we're going to look at how we visualize these things in 3 dimensions. All right, so like I said, I think that's good enough for now, so I will catch you all in the next one. Cheers.